This is Paul Gregg, and this will be part 6 of my backyard roller coaster STEM course on physics, math, and engineering of roller coasters. So we've kind of gone through the physics and a little bit of math to know how to, and the energy relationships between potential and kinetic energy. And now we're ready to build a kart and a roller coaster, simple 2D track. And so I'll assume you've built the track and it turned out a certain way and you have a kart that'll safely run on it. And the things we need to know, it's a pretty simple track. Looks like this. It goes down through a dip, over a peak, down through another dip, and then at some point stops and turns around and goes back and forth a little bit. So we did analysis on this using a spreadsheet to see what we'd predict, but what we really want to know is what, with the real geometry of the track, what we're going to see. And this was just a model track that some students built. So these numbers have all got to go change to what you really build. The beginning height, we have kind of a zero line here, and then what's the starting height of this, where you start. That'll determine how much potential energy you have. In this case, 64 joules. By the equation mass times height times mgh. Potential energy equals mgh. Mass times gravitational constant 9.81 meters per second squared, and height in meters. Keep all your units the same metric. And then we need to know at the what is the height of dip number 1, what's the radius at dip number 1, and the length of track we traveled between the start and dip number 1. So the length of this track, the radius here will tell us the centripetal accelerations in the downward direction, adding to gravity. And what is the height here? The height difference will tell us how much potential energy we lost and gave it up to kinetic energy. So this first calculation is going to be neglecting all drag. And so in reality, the car, if there was no drag at all, if there was absolutely no mechanical friction and you were in a vacuum, the cart would go down and up and down and up, and then go up here, turn around, and go back exactly to the spot that you started, because energy is conserved. And if we didn't have any changes in energy due to friction or aerodynamic drag, then it would just keep going back and forth forever like that, because it would just be all kinetic or potential energy and no changes to heat via friction or aerodynamic drag. But so just to make things simple, we go through this first, and then we come up to this next peak, the difference in height here. We'll want to know that. We'll want to know the radius there, so we can calculate the possibly negative g's that will how much centripetal acceleration offsets gravity there, and how weightless we really feel. And then we'll do the same thing for this second dip and see what the height is. And this is some students, boys and girls, built this track, and this is what they came up with. But you'll be putting your own numbers in here. So you need to know all of this information for your track, the real information. The height of the hill number 2, radius, on and on and on. And finally, the height, the distances. You don't really know the distances for this calculation, but when we talk about drag, we'll do that. So this is, you want to make a chart like this, fill your numbers in, the heights, the potential energy, 64. Then we go down to almost all kinetic energy here. There's only a little bit of height, and then it goes back up here. We have some kinetic energy, but we get some potential energy also because we've gone back up and are going slower. And then down here, it's not quite as low, so we have kinetic energy is not quite as high, and the potential energy is fairly small. And then finally we'll go up, and if we were really going to not have any friction or drag, it would go back to the same height when we started. It would go back up to 2.17 meters. We still have our 64 joules of energy, and we wouldn't have any velocity, so no kinetic energy when it stopped at the end. So I calculated velocity in meters per second. We go up to 6.32 meters per second, not quite as fast over here, almost as fast down here, and then we go back to 0. So our total energy, neglecting all drag, stays the same through the whole thing. Okay, so now if we include drag, this is what happens. At the start, we still have no kinetic energy, all potential energy. And then we go down here. We do the same thing as we did on the last page, except we lose, we don't really lose, we change a little bit of energy to heat through friction and aerodynamic drag. And for instance, I think they ran the cart one time, and they decided what height it was at the end. And it's a fairly inefficient cart. Remember, I wasn't happy with the wheels on this cart, and it was fairly inefficient. So the height at the end was 0.559 meters. They measured, the kids measured that. And then, so the potential energy at the end, according to MGH, was 16.5 joules. So we lost the difference between these two, which 64 minus 16.5 is 47.5 joules of energy converted to heat via friction and aerodynamic drag. So we converted 74, just go running this cart one time, we converted 74.2% of our available energy to heat. And that's fairly inefficient. And total distance was 8.58 meters, the whole distance of going like down this track to the end where it stopped. So the average energy converted to heat via friction and air drag is 47 divided by 8.585, which was 5.522 joules per meter. And it actually changes as you go along there, but the average would be this. So now, including drag, we do the calculations again. This table is expanded. We have the heights that happened during this run. We have the potential energy, and then we have the distance down the track. We have the drag energy. So as you go down the track, you're going kind of fast. This is a long run here, so you lose a lot of, you change a lot of the energy to heat through friction and aerodynamic drag. And you can see what those numbers come out to be. At the kinetic energy, we have quite a bit of kinetic energy here, less here, less here. It's not going as fast. And finally, we end up, when we're stopped at the end, with 0. The velocities with drag, you can see we're going pretty fast in the first dip, not so fast over the peak, and slower speed through that last dip. And this is what really happened. And so with this very inefficient cart. So here's the kinetic energy plus the potential energy at the bottom. So now we want to see, we've kind of redone these calculations and seen what we think the velocities are going to be at different spots. So it'd be what's interesting now is we need some way of determining what the velocity is here, what the velocity is here, and what the velocity is here, and then we'll know how accurate our analysis was and how if you build a good cart and you run on it, it's going to go faster than this little cart, and you'll save a lot more energy for the end, and it'll be a little different. But no matter what you do, you want to check things out. Check your analysis. So what do we need to measure? We need to measure the weight of the cart and the weight of the rider, and we just need a scale for doing that. We'll work in kilograms, but you can do it in pounds if you really wanted to. But to keep the units straight, it's we'll measure the mass in kilograms. We need some kind of way to measure the height of the different parts of the track, a meter stick or a measuring tape, and then we want to measure velocity. Down here is we'll talk about velocity in a second, but we can also measure accelerations. Many of the newer smartphone apps, there's several of them, but one called Physics Toolbox that I like, and you can actually measure the accelerations. I think there's an Apple Watch, and it measures accelerations on a roller coaster and things like that. But so you can tape your smartphone to the cart and then actually measure the accelerations. If you want to know what the slopes are, it helps when you're building the track. There's a bubble level app in an app called Smart Tools on a smartphone, and you should take a look at that, because if you want to know what degree should I cut this board, you can measure it with a bubble level right on your phone. It tells you 32 degrees or something, whatever it tells you. So velocity, how do we measure velocity? We could get a radar gun. I think there's Hot Wheels radar guns for toys. There's police. If you know a policeman, he may have a radar gun that can do that. There's people that measure the speed of a baseball, and they have a little speed gun they can use. And so you can look at something like that. There is a speed GPS app for a smartphone, but I don't know how accurate that would be. You could try it and see how it works compared to the other ways of measuring speed. You could put light triggers or mechanical triggers and a timer run by a controller like an Arduino, and you could measure over a meter in the first dip. You could mark out a meter and put 2 triggers on it and see how much time it was between the trigger. And you take the distance divided by the time, and would be the average velocity over that 1 meter distance. Now, this is interesting. You can take photos from the side, and you can have rulers in the photos. And there's an app called Seconds Count, and I really like that because, I'll show you a little bit more about it in a minute. You could do slow speed video and count the frames, or come up with another idea for determining what the speed is in different places. There is an app called Tracker, and it's at this website, and I don't know how accurate it is, but it seems very nice. What you do is you go through a video, you input a video to it, and then you put little markers in the video. Okay, and then it will graph what the velocity and accelerations are at those different spots. It's quite powerful and very interesting. So check that out. It's an app. It's a program, free, called Tracker. This is one I like. It's called the Seconds Count app for smartphones. You can determine the velocity of anything moving in a field. You hold your camera steady on something, and things whiz by. And what it does is it reviews. It takes a video from the side, and then you have something in the video that you know is a certain distance long, 1 meter, 2 meters, whatever. You have a physical markers in there that you know how long it is. You review the video, and you can kind of time step through this video and move this thing back and forth, and the video goes back and forth. So in 1/1000th of a second, which is fairly accurate for non-scientific equipment. So you can measure the time between one frame and another frame, and if you have some kind of known distance in there, then you can calculate the average velocity. And we want to compare that to our velocity predictions via analysis. So check out this Seconds Count app for a smartphone. There's also the reason your phone can tell you how many steps you've walked and things like that is it has 3 accelerometers inside your phone. They're little tiny devices. They made them really tiny. But what it does is you have I like an app called Physics Toolbox, and it just tracks the accelerations in the X, Y, and Z direction, and you can look at the app and see which directions on as you hold your smartphone, which directions X, Y, Z correspond to. So you can start this. Tape your smartphone to your roller coaster cart, and let it run. And don't give it a push if you're just trying to compare to the analysis. If you give it a push, obviously it has more accelerations, and you have to kind of account for that. So you just let it go and track the X, Y, Z. I think X is up here, and X is sideways, Z is up and down, and Y is forward and aft, I think. Probably it looks like from this data. And then it plots your acceleration in meters per second squared. And this is 1g. Of course, 9.81 meters per second squared is the gravity, what you feel when you're standing on the Earth. Anyway, it'll sometimes you have to filter the data out, because sometimes accelerations are funny. If it'll track an acceleration that's less than 200 milliseconds, but your body can't really. That's too quick for your body to react to. You can't feel that. When you jump off a step, you can experience 15 Gs. I've heard, but it's for such a short time that your body doesn't really react to it. If you experienced 15 Gs for 30 seconds, you'd black out. You might die if you did that for a minute. So the accelerations at less than a fifth of a second, 200 milliseconds, are much different than longer duration accelerations. So you can play with this, and you can kind of check and see if the G's you predicted in your analysis are anything close to the positive and negative G's. And you can't go negative here. This is negative half of a G or something like that. So I'd be interested. I think you need a newer phone. Some of the older phones top out at 2 Gs or 4 Gs, and so if you're really going to have a lot of Gs, I think you need one of the newer phones. And you can find the limit that your accelerometers are limited to in your. If you see a lot of the data and it goes up and a lot of it hits the same line and goes across, you're probably your phone's limiting the data from the accelerometers in your phone. Anyway, this is a good way to determine and see how your predictions went. And I think we'll leave this for another section. So that's the end of this section, and we'll pick it up, I think, one last time and cover the last things.